the promises and problems of nuclear power. So what is nuclear energy? Nuclear is an adjective coming from the word nucleus. As you know, every atom has a tiny core called the nucleus. It's surrounded by one or more orbiting electrons, and it's those electrons that are going around the nucleus that determine the chemical properties of any given element. All the chemical energy that we're experienced with involves only the exchange of electrons. So if you have battlefield munitions or a raging forest fire, these are all examples of chemical energy. But nuclear energy comes from the nucleus, and the power, the forces that hold the nucleus together are millions of times more powerful than any other force in the universe. They are the most powerful forces in the universe. So when the atom itself, when the nucleus of the atom is able to release its energy, then we have much more powerful release. Here, for example, is the city of Hiroshima, which was destroyed by a single uranium bomb, just one bomb. And this bomb was dropped in August 6, 1945, and it was due to the fissioning of uranium atoms. There were only about 30 pounds of uranium involved in this bomb as an explosive power, and only a fraction of that, perhaps 1 kilogram of the uranium, actually underwent nuclear fission in order to produce this gigantic explosion. So we have here a very powerful energy source, and it's only natural that scientists would be interested in seeing if they could harness this energy for other uses. So here we have the Point-Lepreau nuclear reactor, not very far away from St. John on the Bay of Fundy. And it's a CANDU reactor, which stands for Canadian Nuclear Deuterium, CANDU. The DU is for deuterium uranium. So deuterium refers to heavy water, which is a very special kind of water, not radioactive, that is used in the Point-Lepreau reactor in order to get a reaction going with plain unenriched uranium, the uranium that's mined out of the ground. So here's how a CANDU reactor works. In the core of the reactor, which you can see there as that squarish looking thing, uranium atoms are split in the core, and this produces a great deal of heat. That heat is used to heat up the water to a temperature of approximately 300 degrees Celsius. However, because the tubes are under great pressure, the water does not actually boil at this point. It's superheated water, it's called. That hot water is pumped to the boiler, the steam generator, and there's actually several of them in a nuclear power plant. And in that steam generator, ordinary water, not heavy water, is on the outside of the pipes inside, and they boil. The ordinary water boils because it's not under pressure, and this creates a very large amount of steam. That steam is fed into a turbine where it spins the blades of a turbine and generates electricity. As you may know, most of the electricity that we have comes from spinning wheels. If we use the water from a dam to turn the wheels, then we can generate electricity that way. If we use a coal-fired plant, we can boil water and use the steam to spin a steam turbine and generate electricity that way. So in essence, you could say that a nuclear reactor is just another way to boil water. Basically, that's what it is. Now, nuclear fission comes about when a neutron, a subatomic particle, strikes the nucleus of a fissile uranium atom, which happens to be called uranium-235. Uranium-235 is the only substance in nature that can be used to make an atomic bomb. That's what the Hiroshima bomb was made from, uranium-235. It's the only material that can be used to make an atomic bomb that comes from nature or to fuel a nuclear reactor, as we do at the Point-Lepreau reactor. And when a subatomic projectile called a neutron strikes the nucleus of a uranium-235 atom, it splits into 2 or 3 more pieces, large chunks, which are called fission products. And these fission products are actually new atoms, smaller than the uranium atom, which are highly unstable, and hence we call them radioactive. So we get these radioactive byproducts, which are the fission products, and they are intensely radioactive, and there are hundreds of different varieties. In addition to the fission products, there's also more neutrons given off, 2 or 3 more neutrons. And that's very important because that's what allows the energy release to be multiplied very, very rapidly. And so in less than 1/1,000,000th of a second, you have billions and trillions and even quadrillions of times more atoms being split by these extra neutrons. And that leads to, if it's uncontrolled, it leads to an enormous explosion, such as the Hiroshima bomb, or if it is controlled, and it's controlled by controlling the neutrons, then you can get a steady production of energy, and that's what happens in the Point-La-Perle nuclear reactor. This is a Russian monument to the splitting of the atom. The Russians are very good at building these monumental structures. The man in front of this monument is called Kurchatov, and he's the father of the Russian atomic bomb. And the gigantic sculpture behind him shows the two hemispheres of a broken uranium atom, surrounded by semicircles which symbolize the energy that is being released when the atom is split. And those two hemispheres really symbolize the fission products, the broken pieces of uranium atoms that are given off when you split the atom. Now, I'm going to go through this rather quickly. I want to emphasize to you that there are literally hundreds of brand new radioactive elements created inside the nuclear reactor, elements that were never seen on Earth before 1940. And I have a list here of 211 of them. I'm just going to go through the pages one by one. And the next. And they all have different names: tellurium, cerium, praseodymium, samarium. Here we have hafnium and lutetium and tungsten. All of these are radioactive varieties of elements that already exist on Earth in a non-radioactive form. So on Earth, before 1940, these same elements existed, but in a non-radioactive form. These ones are highly unstable and consequently radioactive. And when we come to the end here, we have what are called actinides. There's plutonium, neptunium, americium, and curium. These are newly created elements which are heavier than uranium. They're sometimes called the transuranic elements. And when we finally come to the end, we have a list of 211 man-made radionuclides contained in 10-year-old irradiated nuclear fuel. That means that this is fuel that was taken out of the reactor 10 years ago. And this is there's already still 211 varieties of radioactive materials. Now, there are probably many more hundreds of radioactive materials. Some of them have disappeared in the 10-year period because they disintegrate. And I'm going to explain what radioactivity is. Radioactive atoms are ones that literally disintegrate or explode. And some of them have very short half-lives, which means they disappear in the wink of an eye, and some of them last much longer. But in any event, it's important to realize about what a multitude of man-made, human-made elements are created by the nuclear fission process. So what is radioactivity? Well, most atoms that we encounter have nuclei, that is plural of nucleus. Most of the nuclei of atoms around us are stable, which means they remain the same forever. So for example, if I have a glass of water in front of me here, the water molecules are H2O, two hydrogen atoms combined with one oxygen atom. That hydrogen atom was around hundreds of millions of years ago and might have been in the flesh of a dinosaur, but it's the very same hydrogen atom. It's just entered into different combinations and has come down to me in this glass of water. Now, a radioactive atom will literally explode or disintegrate. And when it explodes, it gives off what you might call subatomic shrapnel. Technically, we call it atomic radiation. And the atomic radiation can be of two kinds. It could be a particle, and there's an alpha particle, which is positively charged, or a beta particle, which is negatively charged, or it could be a ray, a gamma ray of energy, which is like an X-ray, but much more powerful. And that's what we call a photon. The important thing to know about these emissions, and here we can't see these emissions. In fact, they're invisible to our 5 senses. If we looked at a lump of uranium, it would just look like an ordinary rock. But if you put it in a cloud chamber, then you can see the tracks of these emissions, this atomic radiation, all 3 forms of them, alpha, beta, and gamma. You can see it coming off constantly from this rock. Those are the emissions which can harm all living cells. If living cells are affected by these emissions, then what happens is that the alpha, beta, and gamma emissions will actually break apart the molecules and cause damage to the molecules. It'll break chemical bonds randomly, and it will do this with DNA molecules. So you will have damaged DNA in those cells, and consequently, the cells could, in many cases, just die and be replaced, or in other cases, they may continue to reproduce, but with damaged genetic instructions, and those can become cancers. So there are 2 types of nuclear energy that we're talking about here. Please don't get them mixed up. The first one that we talked about was nuclear fission, and the second one we talked about now is radioactivity. Nuclear fission can be controlled by controlling the neutrons that are given off, and radioactivity, however, cannot be controlled. Once you have a radioactive material, it's going to continue to give off these radioactive emissions, and there's no way known to science for stopping these emissions from occurring. So radioactivity can't be shut off. The word becquerel is used as a unit of radioactivity. It means 1 disintegration is happening every second. 1 disintegration every second. So for example, the permissible level of radioactive tritium in drinking water in Canada is 7,000 becquerels per liter. So just think about that. 1 liter of water, imagine if you had a liter of water in front of you, and if it had the maximum amount that is allowed of tritium, radioactive tritium, there would be 7,000 disintegrations occurring every second in that water. If you then drink that water, then that radioactive material goes inside your body, and those 7,000 disintegrations per second are happening inside your body. Radioactivity is a form of energy that cannot be shut off. That's why we have a nuclear waste problem. The problem is, what do we do with all these things? We didn't want them in the first place. All we wanted was the energy. All we wanted was to boil water, to create steam, to create electricity. We didn't want these things. And by the way, nuclear scientists who work in nuclear plants don't think about these things most of the time, because that's not what they're interested in. They're interested in getting on with the job. And so for the first 30 years of the nuclear age, politicians and ordinary members of the public did not even realize that there was a problem with radioactive waste, because it was never talked about. Everybody simply said nuclear power is clean energy, but it's not really clean. In fact, this material that is produced as a byproduct is the most dangerous industrial product ever produced by any industry on Earth. Now, this is the thing about, you often hear the word radiation, but radiation is not the right word to be thinking about. It's better to think of the word radioactivity, because radioactivity refers to material things. These are actual elements that go into the body. They have many pathways through the environment and through the human body. For example, radioactive cesium goes to the muscle tissue or the meat, and there it disintegrates and causes harm inside the body. Radioactive iodine goes to the thyroid gland and can cause thyroid damage. And in fact, for that reason, because of radioactive iodine given off by the Chernobyl plant, 5,000 children in Belarus had to have their thyroid glands surgically removed. So these are chemical substances which are also radioactive. And again, these chemical substances have non-radioactive counterparts in nature. Iodine, for example, is a naturally occurring non-radioactive material. And it also goes to the thyroid gland, but there it actually is medicinally helpful because it prevents a disease called goiter. Radioactive iodine goes to the thyroid gland, and it also prevents goiter, but it also kills the thyroid gland. So chronic exposure to radioactive materials is known through many scientific studies to increase the incidence of cancer, leukemia, and genetic damage. Genetic damage means damage to the eggs and sperm of a woman or a man, which then can result in children or offspring who have genetic damage in their chromosomes. It can also cause anemia, and does. It damages the immune system by compromising it, basically by getting rid of the white blood cells. It also can cause strokes, heart attacks, and even in unborn children, if they're exposed in utero, it can cause low intelligence. And this has been well documented, both from fallout from the atomic bombings, but also from medical studies of pregnant women who have been x-rayed during their pregnancy. But there is a latency period for most of these effects. The onset of disease may occur years or decades after exposure. It's very similar in this regard to cigarette smoking. You don't see people keeling over dead from smoking a cigarette. They look like they're having a lot of fun. But if you look at the statistics, you find out that many years later, they have 10 times as much lung cancer as people who are non-smokers. It's a very similar thing with radioactivity. At low levels of exposure, you don't see any immediate effects. So the effects take many years or decades. In the case of lung cancer, there's a latency period of about 20 years before you begin to see an increase in lung cancer following radiation exposure. Now, this is from an industry ad, a Canadian Nuclear Association ad. It's called Small Wonder. And the actor is holding a simulated uranium fuel pellet, and he's basically saying, isn't it wonderful how much energy you can get out of this fuel pellet? It's like a carload of coal. But what he doesn't tell you is that, yes, you can get that energy out of the fuel pellet, but when you're finished, you can't throw it away. You have to keep your eye on it for the next 10 million years, literally. And if you see these CANDU fuel bundles in front of this gentleman, these are the CANDU fuel bundles that go into the nuclear reactor. Before they go in the reactor, they're quite harmless and they can be handled safely. But after they come out of the reactor, they're millions of times more radioactive because of the fission products, and they would kill any human being in 20 seconds at a distance of 1 meter just by the gamma radiation, the blast of gamma radiation that comes off a single fuel bundle. Now here's the face of a CANDU reactor. This happens to be the reactor in Darlington, but it looks very, very much like the face of the Point-Lepreau nuclear reactor. The man who's standing there, if this is before the reactor ever started up, it didn't even operate for a single day. If he was standing there after the reactor had operated, he would be dead because the gamma radiation from the fission products would kill him, and you can't turn off the radioactivity. You can turn off the fission process by stopping the neutrons, but you can't stop the radioactivity. As a matter of fact, even after the fuel comes out of the reactor, it has to be cooled for at least 10 years in a deep pool called a spent fuel bay. And the circulating water keeps the fuel from overheating. Now, it would spontaneously overheat without that water and would damage itself. It would cause damage to the fuel cladding, the coating on it, and you would get dozens of radioactive materials released as gases and vapors that would go into the atmosphere. And these would be dangerous radioactive releases that would, once they got out into the environment, they would condense and settle onto pasture land or onto buildings and cause radioactive contamination of the surroundings. Even when they put this fuel underground, these are a series of pictures from Atomic Energy of Canada Limited, who did a study on the geological disposal concept, the idea of putting these things deep underground and that maybe they will be safe there. Well, when you put them underground, they're hot, and that's what the red is. The red is the heat of the fuel, even if it's buried 70 years after it came out of the reactor. So that's giving it a 70-year cool down period. It's still generating heat. Why? Because those atoms are still disintegrating. And when they disintegrate, that's a form of energy. And that energy is turned into heat. Here's what the picture looks like after 4,000 years after burial. The heat has spread through the rocks because it's got nowhere else to go. And so the temperature of the rocks are heated up. Here's the picture after 8,000 years. That heat is still, now it has already peaked and it's already starting to diminish again. But nevertheless, you can see that it's a problem for quite a long time. In fact, according to this sequence of diagrams, which are based on math studies, mathematical models, the period that it takes the rocks to return to pretty close to their original temperature is about 50,000 years. And that 50,000 year period is called the thermal pulse. Pulse. You know what a pulse is? A pulse is like a blip on a radar screen. And the reason they call it the thermal pulse is because 50,000 years is just a drop in the bucket when it comes to the toxicity of these buried wastes. Now, this graph is from a report, a Royal Commission of Ontario report on nuclear energy that was published a long time ago, back in 1978. But they did some calculations and they asked this question. They said, suppose you took just 1 year's worth of used CANDU fuel from just one reactor, for example, the Point Lepreau reactor. And if we just look at that fuel, that after it comes out of the reactor, let's look at how toxic it is over a period of 10 million years. And that's what this graph is. The time axis is at the bottom. It goes up to 10 million years, and you can see that the blue line is the total toxicity. And the red line is only the fission products. So you can see that for the first few hundred years, for the first 1,000 years or so, the blue line and the red line are following each other very closely because the toxicity is mostly due to the fission products. When I say toxicity, I mean harmfulness to the human body. And especially toxicity refers to internal ingestion. If you happen to eat food that is contaminated or drink water that is contaminated or breathe air that is contaminated, then these materials get inside your body and they can irradiate you from inside. So this stuff remains dangerous for 10 million years. And in fact, the first year it comes out of the reactor, how much water would you need to dissolve this material, these fuel bundles, from 1 year's operation down to the level of maximum legally allowed contamination? There are limits on how much you can contaminate drinking water. And if you ask how much water would be needed to dilute this waste down to the level of maximum pollution, the answer is you would require approximately the volume of Lake Superior to do that. So you can see why people are very concerned about making sure that these radioactive materials do not get into the environment, because they are extremely harmful if they do escape. And that's what happens in a nuclear accident. Some of these materials do escape into the environment, and the result is you have contaminated land that remains contaminated for a very long time. Now, there's one other thing. You might wonder, why is the blue line and the red line on the graph back there? Why are they different? Well, because there's other materials that I didn't tell you about. I only told you about the fission products. Remember the fission products? Those are the broken pieces of uranium atoms. But there's something else going on. Remember those extra neutrons, the extra neutrons that are released when a uranium atom splits? Well, some of those extra neutrons go on to create what are called transuranic elements. These are elements heavier than uranium. When, for example, when a neutron strikes the uranium-238 atom, it does not split. Instead, it turns into an atom of plutonium. Plutonium is a brand new element that never existed on Earth before. And in fact, to this day, the only place you'll find plutonium in the world is places where we humans have made it, because it's a totally human-made element. But it turns out to be one of the most powerful nuclear explosive materials. And in fact, it is used in nuclear weapons now, and it could be used for nuclear weapons for many, many thousands of years to come, because the half-life of plutonium-239 is 24,000 years. That means it takes 24,000 years for just half of the plutonium to disintegrate and turn into something else. So you can make bombs out of plutonium-239 now, or 1,000 years from now, or 10,000 years from now, or even 100,000 years from now, and we don't know how to destroy it. We really don't know how to destroy it, although in New Brunswick, there are 2 new reactors being proposed, which claim that they will be able to fission some of these plutonium atoms inside the reactor, and that's one way of getting rid of them. But of course, if you fission them, you then produce fission products, which again is more radioactive waste. So you can't get rid of these things without simultaneously creating more radioactive waste. As I said, plutonium doesn't exist in nature. I have here a bilingual slide here. It's created as a byproduct of uranium. Actually, every atom of plutonium started off as an atom of uranium. And the first 2 atomic bombs, the one that was dropped on Hiroshima on August the 6th, and the one that was dropped 3 days later on Nagasaki in 1945, the first one in front was made of uranium, as I told you before, highly enriched uranium. But the one in the back, the roundish one, was made with plutonium. And nowadays, plutonium is the main nuclear explosive in the world's nuclear arsenals. And when they dismantle a nuclear weapon, what they do is that they take the plutonium out of the weapon, and then it's no longer a nuclear weapon. This is how much plutonium is needed to destroy a city. This glass ball was manufactured to be exactly the same size as the ball of plutonium in the bomb that destroyed the city of Nagasaki. It weighed about 6.2 kilograms. That's all the amount of plutonium that you need to make a bomb. I've done a calculation with CANDU used fuel. There would be enough to make literally hundreds of thousands of atomic bombs from the plutonium contained in used nuclear fuel from CANDU reactors here in Canada. So these things have to be guarded, and they even have to be inspected. There are inspectors that come all the way from Vienna to inspect the spent fuel at the used fuel at Pointe-le-Preau to make sure that nobody is getting their hands on that plutonium. They do this in every country of the world that has nuclear reactors. Now, this is a drawing of a friend of mine who also was the photographer of most of those black and white pictures you've seen. His name is Robert Del Tredici. He's a good friend of mine. And I mentioned to him once, he said, why can't they just take the plutonium and make a bomb with it? And I said, well, there's a firewall. And so he drew a literal wall of fire to indicate this firewall that separates the used fuel from the reactor from the bomb. And that firewall is radioactivity. As I told you before, a used fuel bundle is so radioactive, it'll kill any human being in 20 seconds at a distance of 1 meter. So how on earth can you possibly steal a fuel bundle and expect to get the plutonium out of it? You're going to be dead before you get out the door. So that's the firewall. The firewall is intense radioactivity, which does not allow you to have access to that plutonium. Many people in the nuclear industry would actually like to get that plutonium, not for bombs necessarily, but for fuel. They say that we could use that plutonium as nuclear fuel, and it's true. You can use it as fuel. I told you before that the only naturally occurring element that can be used for fuel is uranium, but this is not a naturally occurring element. The only problem is if you build a reprocessing plant to separate the plutonium, to extract the plutonium, then it becomes a lot easier to make a bomb because you've eliminated the firewall, or at least you've eliminated most of the firewall. And consequently, you now have a real problem of proliferation of nuclear weapons. We don't know what we're going to do with this waste because we don't have a solution anywhere on Earth at the moment that is actually approved. But if you close the cycle, these materials available that could be used for fuel, but it could also be used for bombs. And the problem is if criminals or terrorists are able to steal some of that separated plutonium and divert it for criminal purposes, then you could have homemade atomic bombs that could be set off in any city at any time, and nobody would even know who did it. So we've come to the end of our time. This is a picture of a young Kazakh woman in Kazakhstan who've just learned that high-level radioactive waste was dumped into the Techa River that flows past their village decades ago, explaining a rash of diseases that have been observed ever since among the village people for decades and decades and decades. And the scientists in Russia were not allowed to use the word radioactivity. They coined the word vegetative sickness. and they said that people were dying of vegetative sickness. But what it really was radiation. So I just wanted to, this is fighting climate change by reducing greenhouse gases. We do have renewable energy like wind power and solar energy, and we have nuclear power, which neither of which release greenhouse gases, and consequently both of them could be considered competitors for clean energy. But as we've seen, nuclear power it's crazy to call it clean energy. To call nuclear power clean because it doesn't produce carbon dioxide, which it doesn't, would be the same as calling coal clean because it doesn't produce plutonium. It doesn't make any sense. It's not clean. It's just not producing carbon dioxide, that's all. It's very dirty. It produces these very long-lived radioactive waste, and we really don't know how we're going to manage them for the next 10 million years. That's it, the end. So thank you for your patience in listening to all this, and I'm open to your questions.